Okay, so before we start all the organic reactions, just going over the terminology. A lot of it we've done on previous ones, and some of them are new. The first ones here are new. So when we're doing them, there's a certain. I'll have like the mechanism must be known in red if it has to be memorized, and you'll have to know the mechanism. So these are the ways that we do it. We always go the electrons doing the moving. And if it's a double arrow like this, it means both electrons are going over here. So this will become positive with no electrons, as you can see. Now, if we're doing, that's called heterolytic fission, which is on a separate slide coming up. If there's one electron to one side and one electron to the other, it's this half arrow. So you can see that is being created there, and they're both radicals. So to combine lots of terminology there. Okay, so the radicals we've done a few times. So if it doesn't have a full valence electron shell, it is highly reactive. When you do a big dot like this, it's going to react with the first thing it comes in contact with, either to form a covalent or ionic bond, one or the other, or something else. Okay, square brackets we've done with Lewis structures, Lewis dot diagrams. So that charge represents the charge overall for what's inside. And we've done dashed lines with resonance or hybridization, at least for the high levels. And so that's just electrons spread over several bonds, definitely for graphite, that we've talked about that, and for benzene. So we've talked about it for standard levels as well, but a lot more detail for high levels. So for homolytic and heterolytic fission, if it's homo, it's the same. So that split is less common, and it's the same. So the two products look the same, and they're both radicals. We'll go into that in a bit more detail with alkane reactions. And for heterolytic, they're different. So heteros are different. You can see differences. So either one side gets all the electrons and the other doesn't, or vice versa. So radicals, just to meet up with your syllabus requirements, because they've been quite specific. So there's an atomic radical, there's a molecular radical, there's a radical with a negative charge, and there's a radical with a positive charge, cationic, anionic radicals. All right. Moving on. Nucleophiles. So things that like positive are negative. Okay, so this is a nucleophile because it has a lone pair, so it's negative, and it's attracted to that, which is an electrophile, likes electric, so it's positive. So this is usually the positive end and the negative end. Okay, so neutral nucleophiles, well, they'll have lone pairs somewhere. So and there'll be also the negative end of it for all of this stuff. So they're lone pairs and the negative end. So that's the nucleophile, because it's the negative bit that's attracted to the positive bit. And here, same thing as here as well. There'll be the negative bits. It won't be this positive. It won't be this positive end. It'll be this negative. So it's an anion. So it's really the same deal. It's the positive end of the molecule, whether or not it has a charge, and it's an anion or not. Okay. And so we can move on to the other one, which pairs. The electrophile is same but opposite. So that's because London dispersion forces with this one, but that there could be a nucleophile or an electrophile depending on what end it was attacking with. And so that one's just a positive. The nitrogen is less electronegative, so that'll be the pos end there. So that'll be the electrophile end. And the carbon, as we saw, a positive carbocation, it'll be the central carbon bit that's the electrophile. Okay, so it likes the negative bit, so it must be the positive bit of that molecule. We've touched on those before, and so that's all the terminology. Now we're going to start doing reactions.